share my screen here. Okay. Okay, can you all see that?
Yes.
Okay, great. Okay, so again, good, awesome. Okay, so again, limits to growth is a very common archetype or structure in system dynamics. You'll see it in many different types of models and contexts. So knowing how to build this basic model type is very helpful because it's something you can draw on for a range of different problems, right? And basically what this refers to is when a population or an organism or an institution or anything is growing. And while it is growing, it creates conditions which then inhibit that growth, right? So you can think of it as, for example, bacteria in an Erlenmeyer flask or a beaker, that as the population of bacteria in that flask is growing, they're producing waste products, which then start to poison the population and limit that growth, right? This can be applied to human population. It can be applied to, the oil sector, right? Be relevant for Nigerian audience that as we're producing more oil, there are more oil spills, which create problems and backlash to that industry. So as something grows, it's creating conditions that inhibit that growth. That's the basic limits to growth model. This is a very, very famous model that was developed by a very famous group of system dynamics modelers back in the 60s and 70s. So there's a lot there. I'm not going to get into all of that now, but you can read books about this if you want to. Jürgen Randers, Donella Meadows, and Dennis Meadows, for example. Okay, so basically what this model structure looks like in a causal loop diagram format is that you have a population that's growing. And I think we've talked before about, reinforcing and balancing loops, right? This audience, I hope, is familiar with that terminology. So the bigger the population, the more growth that you have because you have more people having more babies or more bacteria reproducing more or whatever your thing is, right? But then they also are producing effects which lead to those limits, right? So for a human population, it might be as the population grows, you have more pollution, you have more conflict, you have more disease, whatever it is that's then kind of leading to something that inhibits that growth. So the growth is reinforcing and the limits to the growth are balancing. Okay. And so what behavior does this produce? Well, if there are either no limits or the limits are very far off or the limits are themselves growing, you get exponential growth, right? Because that's when the reinforcing loop is dominating. If you have a human population that's growing in a very well-resourced environment and there's basically, at this point, no limits to speak of, you're going to get exponential growth. However, if you have that environment and those limits that are giving instant and accurate responses to the growth, then you're going to see this kind of sigmoid curve, right? Because you're going to have at first exponential growth, and then as the balancing loop starts to come in and dominate, that growth is going to slow until it approaches zero at the limits, right? So again, this is only if you have signals from the limits that are, you don't have a delay effect, right? You have signals from the limits that are immediate and that the growth responds to those limits. And we'll see what this looks like in a minute when we build the model. More commonly, you're going to have more of an overshoot and oscillation pattern, right? And this is what happens when the signals from the limits or the response to the balancing loop is delayed, or you have the limits themselves might change, right? So if you're in an environment where the population is growing, producing pollution, and that pollution itself harms the environment such that then it is less able to accommodate a growing population, then you're also going to lead to this pattern. And an extreme version of this pattern is the overshoot and collapse, right? Where you exceed the limits so far that you degrade the resource to the point where it cannot recover. And we have many examples of this in the real world, from the collapse of North Atlantic fisheries to, the erosion of topsoil in the American plains during the Dust Bowl, where you just overshoot the limits so far that the system collapses and cannot recover, right? And so this happens when there's a significant delay in the signals you're getting from the limits, or when there's extreme degradation of the resource. Okay, so that was a whirlwind introduction. So let's try building a basic limits to growth model. And here again is the patterns, right? So exponential growth when there's no limits, sigmoid curve or S-shaped growth when there's limits but no delay, and then either overshoot and oscillation or overshoot and collapse when there are delays. Okay, I think that, and then, yeah, I just had a few more examples of what this could look like in the real world. So it doesn't necessarily have to be a population. I pulled out a few examples of limits to growth models from the literature. So this one is talking about what happens when you are over pumping your groundwater table, right? So the groundwater is helping your agricultural growth, but then at the same time, you're producing conditions that will eventually inhibit that growth because you're drawing down the groundwater, you're depleting the resource, right? So there's a limits to growth. Or common one is when you have an industry that's growing, right? And as you are creating more customer orders and selling more products, you get more revenue, which leads to new product development. But then eventually your company is going to kind of overgrow its ability to provide these products, and because it's becoming too complex, and you might have a overshoot and collapse or overshoot and oscillation type of thing happening. And then on a personal level, thinking about how you're trying to manage your metabolism, manage your weight, you can also have a limits to growth thing there. So the point I'm trying to make here is that there's a lot of different limits to growth patterns that show up in different kinds of systems. So this is a very common pattern, and it's something that you can reproduce in a system of your choice. Okay. Any questions about that before we try to build the model? And so should I take us to about 10:40, I'm going to say, right? And then Len can take over. Is that about right? I'm just trying to look at the timing here. Any of the organizers want to chime in? When should I try to wrap up?
I think a half an hour more would be great.
Okay, sure. Perfect. Okay. So I will go till like 10:45-ish, and then Len can take over. Okay. And yeah, so any questions? So Victor said challenges of big cities. So right. Okay. So yeah, if you're saying a big city could also exhibit a limits to growth pattern for sure. As a city grows, it's creating complexity and challenges, maybe drawing down resources or creating traffic, right? That's going to inhibit some of the growth of that city. Absolutely. You could apply limits to growth model to that. Any other questions? Okay. All right. Well, let's get into it, and I can show you all how to build a basic limits to growth model. So I'm going to do it in Stella, but if you have Vensim or another modeling platform, feel free to open that as well, and hopefully you can still follow along. The platforms are very similar. You're going to be, especially when we're doing something relatively simple, they're pretty similar. So you should be able to follow along, hopefully. But if you have any questions, feel free to pipe up. I know there's Vensim experts here too, other than me, that can also help. So you can even put something in the chat, and if I don't see it, someone else might get it. Okay, so let me share here, and I will walk us through this.
Hello, Lara.
Yeah.
Sorry to jump in. So I would suggest we populate our questions in the Q&A or in the chat box. So we'll then take everything together towards the end. That way we're able to save some time.
Yeah, that's totally fine. Yeah, that's fine. And just because it is going to be a little bit hard for me to kind of be demonstrating the model and checking the chat, and so if somebody else if somebody puts a question in the chat and somebody else
I'll anchor that.
That would be great. So feel free to answer.
I'll note all the questions. Yeah, I'll note all the questions. So I'll let you know.
Okay, great. But I'm also saying that we have some more advanced modelers on this call, I know. So if somebody puts a question in the chat that somebody else has an answer to, feel free to answer it. It does not have to be me if you know the answer. So great.
Yeah. Awesome.
Okay, sure. Okay, yeah, and for example, I see Abu just asked a question, which is better? Feel free to weigh in. There's different opinions on this, and anyone who's used them, feel free to weigh in, and I'll answer at the end. But for now, let me go into into demonstration here. Okay, let's see. So we are going to build a basic limits to growth structure, and it's going to look like this, okay? So I'm going to do it based on human population. In our poultry model, we based it on poultry population. Basically, we had population of chickens growing, and then things like climate change and crowding, and the confluence of crowding and heat events kind of coming in and limiting that growth. So it is a basic limits to growth model. But for this model, we're going to look at human population. So I got my new model up here. I got Stella. Can you all see that? Sometimes when I switch screens with Stella, it doesn't. You can't see it. Can you see the model page?
Yes, I can.
Okay,
I believe everybody
okay.
can see.
So a short question: do you have to install it on your PC, or can you do it also on the web?
There is a web version, I believe. I have not used it. So if somebody has, please weigh in. You can download a free trial version of Stella. You can also download a free version of Vensim. So there's many different options. But like I said, if you have it in front of you to follow along, that's always the best way to learn. In my experience, if you kind of listen to it, it's not quite as effective. So yeah, so feel free to go ahead and pull that up if you have your modeling software in front of you. That would be great. So I'm gonna reproduce this basic stock and flow structure, which you just saw, right? So we have our stock. Oh, I can't spell. This is always the problem when I'm typing in front of people. Okay, and let me zoom in a little bit here so you can see that a little bit better. Okay, so we have our population here. Okay, that's our stock. Remember, stock is something that is an amount of something, right? That can be growing or declining. And then we have our births flow coming in, and we have our deaths flow coming out, okay? So this is the same thing that we had with our poultry, but in this case, I'm going to say it's like a human population. And when I build a new model, I'm always going to save it. So if my computer crashes, I can recover it. So I will just call this the LTG model for Nigerian SD. Okay. All right, so save your model. All right, so now we have that basic stock and flow structure, but we now have a couple of converters we need to add in too, and then connect it all up, right? So when we have a stock and flow structure with population, we typically have a birth rate and a death rate that help us to calculate the birth and death flows. So we're going to put that in, okay? All right, so I'm going to put those in. Okay. I'm going to have death rate over here. Okay. And then the births and deaths, as you can see, are calculated by multiplying the amount of population by the birth rate and the death rate. So can you see where the feedback loops are coming in, right? Right here, this is a feedback loop, because the more population you have, that's going to impact the births that are coming into that population. So the more births you have, also the more population you have, the more deaths that are coming in, right? Okay. So this is a very basic population model that I'm building here. Okay. Let's make that look a little nicer. There we go. Okay. And now that we have the structure, we're going to save it. We're going to put some numbers in it. Let me pause a minute here, see what the questions are. Okay, great. Thank you, Len, answering the question about comparing the two different softwares. Yeah. I will just say briefly that I like to use Stella for teaching, because I feel like it's a little bit more of intuitive interface for very beginners. But as you get into more advanced modeling, I think they're much more comparable, and yeah. But I often use it for teaching, just because if you're a brand new beginner, I find it a little bit easier to learn on. That's just my opinion. However, it costs money, and there are student versions of it that are pretty cheap, but it does cost money. Okay, any other questions about this basic model structure before I put some numbers in it? Okay, all right, I'm gonna move on then. Okay, so here's the numbers I'm gonna put. Okay. And I haven't put the limits to growth piece in it yet, but I'm just building the basic population model that we're going to use to address this, okay? So I'm going to say that my initial population is 1 million, and my birth rate is going to be 0.012, which is 12 births per 1,000 people. So remember, I can put numbers in my model by clicking on it and then going to the equation tab over here for those of you that use Stella. So my initial population is going to be 1 million. Okay. And I'll put a unit in here. I'll put people. Okay. And then my birth rate is going to be 0.012, like I said. Okay. That is what I said, isn't it? Let me just double check. All right. Yes, that is what I said. Okay. And then, as I mentioned, the births is going to be an equation that is equal to the birth rate times the population. Okay. And the death rate I'm going to set up is 0.004. So that's 4 deaths per 1,000 people per year. Now, I should have mentioned that we're going to be running this on an annual time step. So remember that everything in Stella, because it is a dynamic model, is per time step, right? Per year. Okay, so death rate times the population. Okay. Now I need to set my model run parameters, okay? And I'm going to do that up here under run specs. Okay. I'm going to run the model for 100 years with a delta time of 1 year. Okay. Okay. And I'm going to graph my output so I can see what it looks like. Okay. So I put a graph down, and that's the graph here. And I want to graph my stock. Usually when you're looking at a system dynamics model, you want to see how the stock behaves, because that's typically the variable that you're most interested in. And that's going to exhibit the dynamic behavior that you want to track, right? So I'm going to go down to this box here and say that I want to graph population. Okay. And I'm moving a little fast just because of the, the time crunch here. Hopefully you all are able to follow along. Okay, so now I'm going to run the model and see what happens. What do you think is going to happen based on the model I just set up? Any ideas? So remember, my birth rate is 12 per 1,000 population, and my death rate is 4 per 1,000 population. I'm running it for 100 years. What behavior do you think we're going to see based on what I talked about earlier in the presentation?
I think a nearly exponential growth.
Yeah, good. That's what I would expect, right? Because we don't have any limits. And in this case, the birth feedback loop is going to be stronger than the death feedback loop because the rate is higher, right? All right, so let's see if that's true. Yep, looks like exponential growth to me, okay? All right, now I'm going to put a limits to growth piece in. Any questions before I do that about what I just did or about the model process? Let's see, what's that? Okay. All right, seeing none, let me move along here. Okay. So now I'm going to add a limits to growth piece, right? So this is going to be a piece that pushes back on the population growth, by having an effect on death rates. So remember we talked about like one way that could play out is that as a population grows, it's creating pollution. The pollution may be, you know, causing cancers or deaths of some kind, right? That's the way that it could work. So I'm going to go in here and add this structure where I have a carrying capacity. That's an ecological term, meaning the amount of population that the ecosystem can support. And then I'm going to have that have an effect on the death rate. Okay, so I'm going to build that into the model. All right, so I have my carrying capacity down here. And then I have here, maybe I'll move this so it's a little bit less messy. Connect that up. It's going to come in here. Oh, come here. Okay. And then I also am connecting the population to the effective carrying capacity, because the way that this works, right, is that as the population grows, the effect of that pollution or that, you know, carrying capacity impact is going to be stronger, right? So I have to take both those things into account. So let me put that in there. There's an arrow. Okay, here we go. All right, and now I need to put numbers on it. Need to parameterize that piece of it. Okay. So I'm going to set the carrying capacity of the system at 1.45 million population. To be clear, I'm just kind of making up these numbers as a simple model demonstration. If you were going to do this in a real system, you could try to parameterize this based on real data of some kind. But these numbers are basically made up. So I'm going to make this into 1,450,000. Okay. Now there's many ways to look at this type of impact, the effective carrying capacity and death rates. The way I'm going to do it is through a graphical function. So this might be a little bit new for folks. But basically what I'm going to do is I'm going to set up the impact of the carrying capacity on the death rates. So how strong that impact is a function of how close the population is to its carrying capacity. So, for example, if the population is getting close to 1.45 million, which is the carrying capacity, there's going to be a really strong impact of that on the death rates, which is what this graph is describing, right? So I am going to go in here. Back to Stella. Okay. And the way that we're going to do this is we're going to first enter into the equation box that we want this to be a function of the population divided by the carrying capacity, okay? So I'm going to put that down here. Then I'm going to go to this little graphical tab, okay? Down here, graphical function. And I'm going to hit that I want my, my function to be graphical. And you can then draw what you want the shape of this to look like, okay? So notice that down here on the x-axis, I have population over carrying capacity. That is the independent variable. And then I have the effect of the carrying capacity on death rates up here. And so you see that this is going to vary between about 0 and 2. So in other words, the population can be up to 2 times the carrying capacity or 2 times over what the carrying capacity is. And then the effect of the carrying capacity and death rates is going to vary between 0 and 50. Again, I'm kind of making up these numbers, but I'm trying to make it be like a stronger and stronger impact as this gets higher, right? So I'm going to put this here. This is going to be between 0 and 50. And then Stella has this great little thing where I can basically draw a graphical function, right? And I'm going to make it kind of a curve like this. So you can see that like the effect is 0 up to when population gets about like, you know, I think that's like 60% of what the carrying capacity is. So you can play around with this. You will see that changing this graphical function does have a pretty big impact on what your model is going to look like. That's one of the things I'd love for you to play around with, you know, once I'm done with this. But I'm going to make it look a little bit like that. Okay. Yours might look a little different. That's okay, because the point is to play around with it. All right, so there we go. I'm done with that. Okay, and you can see that because I made it a graphical function, I have a little squiggle here. That's what that means. It's a graphical function. Okay, and then I'm going to make the death rate equal to, oops, come here, come back here. I'm going to make the death rate equal to 0.004 times the effective carrying capacity. So the effective carrying capacity is going to increase the death rate. Okay. Okay. So I'm going to change that equation and put the effective carrying capacity into that equation. All right. Now I'm going to run the model again and see what happens. Okay. Whoops. So now it's a little hard to see with the scale here, but you can see that rather than increasing exponentially, now I have kind of leveled off and have a little bit of a sigmoid growth curve happening, right? So the population is not going much above 1 million. So remember I said that we have more of a sigmoid growth curve when the response to the limits is instantaneous, right? There's no delay in here. I haven't put a delay in the function yet. So as soon as that population hits, you know, a level of that's close to carrying capacity, there's an immediate signal that increases death rates, and we have a decline in, or a multiplier of the death rates, right? So we can kind of see that by looking at, we can see the death rates here, you know, initially go up and then stabilize, which is driving this behavior, right? Okay. Okay. Now I'm just going to do one more thing quickly, and I know I'm going through this very quick, but to see a different type of behavior, let's see what happens when we put a delay in here, okay? So Stella has a built-in function called a delay, and what this means is that the equation or the signal takes a certain amount of time, right, to perpetuate through the system. So we're going to change our equation for the death rate to have a delay in it. And the delay built in is structured like this. There's the input, which is the equation. There's a duration of the delay. And then there's the initial value, okay? So in our case, the input is going to be the effective carrying capacity times the death rate. The delay is going to be, let's say, 30 years. 30 is the time unit, so 30 years. And then the initial value is going to be 0.004 because that was the initial death rate. So let me go in and change that. Okay, I'm going to put the delay in here. And like I said, it's a built-in, so you can find it in the menu over here. A lot of different kinds of delays. We're not going to be worrying about that right now. So like I said, the function is the input, comma, the time, and then the initial value, okay? All right. And you know what? I'm going to make this graph comparative so we can see the difference between the two runs here. Okay. All right. Or the 3 runs we're doing. Okay. So now that I put a delay in there, let's see what happens. And lo and behold, we have now an overshoot and collapse, or overshoot and oscillation. We could run it for longer to see if it's going to recover, if it's an overshoot and oscillation pattern. But you can tell that, you know, it's different than our second run, which immediately stabilized at a level below the carrying capacity, right? In this case, because we have a delay, the population grows past the carrying capacity and then suddenly gets a stronger signal and comes back down, right? So that's the overshoot and oscillation pattern. And then this is our run 1 here, where we just had the exponential growth and we hadn't added in that carrying capacity yet. So right here in this graph, you can kind of see those three behaviors that we talked about over here, which is the exponential growth, the sigmoid curve. It's hard to see the sigmoid because of the scale on this graph, but it is a sigmoid, and then the overshoot and oscillation pattern. Okay. All right. I know that was really fast. Any in like 5-10 minutes, any questions about that? So that is a basic limits to growth model. That's what it looks like. So you can use this to model a wide range of systems, any system in which you have that limits to growth pattern where you have something growing, but then you also have the growth impacting the conditions of that very growth in a negative way. So you can use this in a wide range of contexts. The poultry model, we used it for poultry sector growth, and then we looked at how that impacts things like demand for poultry and crowding and heat impacts that are going to impact the growth. All right, any questions? I'll leave this up here while I answer questions so you all can take a look at the structure still. Or for those of you who have been following along, anything that you're running into, any problems or clarifications as you're trying to build the model? Okay, well, maybe I guess was this helpful? Like, was this at the right was this at the right level here? Because is it over? Okay, I see some thumbs up. I had no idea what the audience is going to be in terms of like your level of system dynamics. So this was like, this is the lesson I do on like week 3 of my class, hoping that was about the right level.
So thank you.
I like this dynamics class, so.
Thank you. It was a quite nice explanation. So I'm sorry I have not installed the Stella already, but I will try it afterwards.
Okay, great. Yeah, that is the thing. If this recording is made available, you can hopefully go back through it, watch it several times, and kind of go through step by step and do it step by step. Because that's the way I would recommend learning it. Yeah, you really have to do it. You have to model by doing. Yeah.
Laura, I have a question. Sorry, I just joined a little bit late. You presented this application and you switched to the PDF file. Will this PDF file be available after this session?
Sure, I can make it available. Actually, I can pop it in I think I can pop a PDF in the chat right now. Let's see.
That's great.
Yeah, just if you're going to cite it or use it, just cite me, please, because this is something I developed for my class. So it's.
Oh, sure. Yep.
Yeah. Just don't. Yeah.
Thank you.
But I will put it in the chat. All right. Well, if there are no further questions, I guess, Len, it can be over to you, unless there's anything else.
Okay, I'm ready. Wait a few seconds here.
Sorry, Len. Thanks a lot, Laura. It was very explanatory. So I believe that's why you don't have any questions yet. So let Len take over and we'll see if there are other questions towards the end of the meeting.
Okay, that works. I am definitely going to have some issues because I'm not at home and I don't have my dual monitor system. So I'm running off my laptop. So please forgive me if you see weird screens as I switch back and forth. So I'm going to do a share screen here, and I can only share one screen. So that's the one that's going to be shared. And now hopefully you see a Vensim copy on the left and a PowerSim Studio copy on the right. Can someone give me a signal?
Yes.
Yes. Okay.
Yep.
All right. Now
Awesome.
I'm going to go to PowerPoint because also, as Laura said, I wasn't 100% sure what might be happening today. So I too am reusing a little bit of training material, and some of you have seen this before. Just a plug for System Dynamics here. And every year at the conference now for I don't know how many years, I've done a webinar called Starting from Scratch. So I've got this nice clean slate in Stella or Vensim or Studio or Insight Maker, and I want to start putting objects on it. And I found in my teaching that a lot of people get really lost when they're converting ideas and mental models from their minds or from paper and putting them into software. So I'm going to try to go through this quickly. First, I asked the question, what is it we do when we create a model? It's only an abstraction of reality. Also, I need somebody to watch the chat. I forgot to say that. Okay, what else are we creating? Are we creating an interface, a flight simulator to allow access to people other than ourselves? Maybe our professor, maybe a client, maybe an organization. What would we like them to see? And when we put that model and that interface together, we have what I call an application. Most of us don't build applications, we just build models. And then finally, and I'm assuming Laura's got students, they probably have to write a report about the model and its results. So I try to think about that before I start working. And here's some terminology I use. Let's say I'm building a model that's a bit bigger than what Laura showed us, and one part of it might be that population. One part of it might have something to do with the economy. This is from my background in surface and groundwater modeling and energy modeling, and I call these modules. So I made a conscious decision as I'm modeling to separate the kinds of things I'm looking at and literally separate them on the screen. Unfortunately, all three of the major softwares do it in a very different way. I'll show that to you. Once I've finished that, I have what I call the model. Then I could put an interface on it and I would have an application. And as I said earlier, you may not be adding an interface to your model. That's a lot of work, believe me. Some working definitions. I call a module a separate part of a model. It can stand alone with little exchange of variables with other modules. So Laura's example of the population model, imagine reusing that in many, many different problem situations. You just change the names of the variables. Obviously, you change the values, but you can reuse that construct. And in the last webinar, I talked about archetypes, of which limits to growth is one, reusable. And a model is just everything you did. All the code, all the variables you created to represent your problem. And finally, an interface is access to the model. One quick question is that, do you see that zoom bar? I hope you don't. Okay, because it was blocking things for me. All right, here we go. Go forward. So when you're building a model, you have different kinds of variables. One group of variables I call is the exogenous. That's data that typically comes from external sources. Laura already mentioned that. We might be getting data from reports, etc. We might have a published birth rate, a published death rate, a published carrying capacity. These are exogenous, outside of your system dynamics thinking. And then, of course, you have all the internal calculations, all your endogenous variables. That's why people engage us to help them solve problems, because we know how to do that. And then finally, well, not finally, but you might also create variables just to enable an interface. And remember, if you're not building an interface, this is not really a problem unless you yourself would like to see the way the data is presented in a different way. And then finally, as you get better at modeling and get more experience, you will find that you'll start creating variables just for testing and debugging both your logic, your mental model, and how good you are at using the tool that you use, you know, Vensim, Stella, Studio, whatever. That's it. So if you have a variable on your screen, my hypothesis is that it's got to fit in one of these 4 categories. Most of us are only concerned with the bottom 2, but as you progress in your skill, it will expand. And we don't know how much you're going to expose to the user. That's why I tried to put some animation there to show. That's a conscious decision by you and your clients. Okay, so if you look up on Wikipedia, how many software modeling packages are there? You'll see a whole bunch. And you'll see packages and you'll say to yourself, I didn't know that could do system dynamics. Well, you can bend and twist it to do system dynamics. But the big 3, I call them, are IC Systems, Stella Architect. There are multiple versions available. There's a 30-day demonstration free version. PowerSim Studio, PowerSim AS is the name of the company. Studio is the product. It also has multiple versions. It has a Studio demo, again, a 30-day limit. And then it also has Studio Express, which is a free, completely free version with no time limit. And then Ventana produces Vensim, again, multiple versions. Vensim PLE is the free version, and there's no time limit. Okay, maybe your tool isn't there, but the concepts are still applicable. I was supposed to skip this slide. So this comes from Nikki Zimmerman's presentation, gosh, sometime in, I think, 2020 or 2021. It's available at the System Dynamics Society website. And she talks about the steps in preparing the problem definition step, you know, identifying key variables, behavior over time. And let's face it, we can't do all that in this session. And then you're going to build stock and flow diagrams, model equations, simulate, and finally analyze what you did. So my exercise was actually a population model for this presentation. And I wanted to say I had an initial population of 1,000 persons, a population, a stock, a bathtub, which is the integral of that growth rate, which we haven't identified, and its initial value is initial population. And then a growth rate of 1.1, and depending on what tool you use, there are different ways to specify what the units are. So it could be 1.1% per year, or here's an example of 0.011 that has a unit of 1 over year. And then finally, growth is simply the population times the growth rate. Okay? And if you can see the top of the screen there, of course, I've already thought about the problem definition. I've identified all my variables. I figured out how long the model would like to run, and I've set the DT, the delta time. So before you do anything, what I'm asking is, have you decided what your time unit is? Are you doing a model that's producing things year by year? Right. Do you have a time step, a DT? And in each of the 3 major tools, this is where you would find that kind of thing. Okay. Has a duration, a start and a stop time been chosen? How long will the model run? Does it start in year 2023 or is it year 1? It's up to you. Have you established a set of units for the model even before starting? Have you thought about that? Are you going to measure humans as persons? Are you going to measure them as people, etc.? What kind of software compatibility do you want to maintain? Almost all 3 of the major products have compatibility issues back in time. This shouldn't be a problem for beginners because you're starting out now. But let's say you're on the internet and you Google something and you find a great Stella model from 1983 and you find out that the current version of Stella won't open it. That's okay. You can contact the folks at IC Systems and they will translate it for you. Have you got a naming convention? How do you name your variables? I base my naming on a memo from MIT that's about 22 years old. And this is how things are named. Stocks have the first letter capitalized of every major word. Flows and auxiliaries are all in lowercase, and constants are in capital letters. And I put this other here as a joke. If you can think of another object, then maybe you can come up with your own convention. Why is this important or useful? If you print out a listing of variables, your reader will instantly know which variables are stocks, flows, auxiliaries, and constants. Got it. Let's skip this last one. Okay, if you just place objects on the screen, here's Ventana's VenSim. This is what you see. This is what you see in PowerSim Studio. And this is what you see in Stella Architect. Okay, couple of things about this. Notice that they're different, and also notice that they're the same. System dynamics as a methodology is limited to 4, maybe 5 different kinds of objects in a model. Okay. Notice that they all use arrows to connect certain kinds of variables, and they use pipes to connect other kinds of variables, right? But even after today, I doubt that any of you would have any difficulty looking at a model in any 3 of the softwares. You would be able to identify that, hey, the rectangles are stocks. These pipe-looking things with a directional arrow on them are flows. And then if you use the naming convention, you would know what the constants were, what the auxiliaries, or Stella calls them converters, were. It's not that difficult because what we're doing here is implementing a method in software. This is not Fortran or Python or COBOL or any other computing language that isn't constrained by a methodology. This is system dynamics. Let's see if I can get my cursor to move. Okay, and as you get into this more and more, especially if you're an instructor or become an instructor, the place I used to work, we developed rules. For example, notice how I have initial population as an external variable here. Our programming team, which was as big as 30 people, said, if the initial value is other than 0, our team requires you to have a variable called initial something. It's just a quirk of where I worked. Okay, now, after you put that on the screen, if you hit x squared in Stella, or fx, f of x in VenSim, you notice that the screen goes black for VenSim. Studio doesn't change, and Stella gives you all these warning messages. Okay, here's the problem. For simple models, not a big deal. What I've seen is students will put 30, 40, 50 variables on a screen and without identifying them, just creating them and placing them on a screen. They go to the definition window, the entire screen gives them an error, and they're now in panic mode. Where do I start? What do I do? Don't model this way, please. I recommend what's called the outside-in approach. Now, the only way this works is if you did some thinking. If you used your protein computer, up in your head to help you plan a little bit. So I add constants first. It distinguishes exogenous from endogenous. It indicates potential opportunities to grow the model scope, right? I might have a variable called, I don't know, system dynamicist's annual salary. And I put that in as an exogenous variable. And someday I'd like to build a model to add on to how that gets determined. That's what I mean by growing the model scope from a constant. It highlights the potential policy variables. What will people be sliding, if you know what I mean? What will they be able to increase or decrease? And then finally, and probably the most important part, is it determines what units you'll be using. Second, I go to add stocks or levels. That sets up unit inheritance, right? So if you add a stock and you've got a constant called initial population measured in people, well, then the stocks unit should be people. Obviously, model transparency. And then I iterate through auxiliaries and rates, and that helps me to manage the logic, reinforce that inheritance of units, and finally, and importantly for us, enforce the SD methodology. You can build non-system dynamics models with system dynamics software. An earlier part of this particular presentation, I analyzed 325 models that were submitted to the conference. There were actually models submitted that had no stocks in them. Couldn't be system dynamics. So we're going to use the outside in. I'm going to go through this quickly and then jump to the tool. We're going to do constants, then stocks, then flows, then auxiliaries. So your screen would start to look something like this in stages. Likewise for Vensim, and likewise for Stella. Okay, if you're writing a report for faculty, for clients, etc., I highly recommend this rubric that comes from what's called the Electronic Oracle. It's a textbook, quite old. You'll get these slides from Bunmi or Kalichi. As you're building, you're filling this in, so that people who don't like to look at so-called spaghetti, they'll be able to read in prose what it was you did, why you did it, when you did it, things of that sort. Now, let me see if I can get out of, yes, I can get out of PowerPoint. Can everyone still see the screen?
Yes.
Okay, great. So, excuse me, on my left, I've got Vensim. And on my right, I've got PowerSim Studio, and I don't have a current license for Stella Architect. So I'm going to go grab a variable here in Vensim A and drop it on the screen. And since I know it's a constant, I'm going to call it initial population. Okay. And then I'm immediately going to go up here to define it. And notice what happened. Those of you who are Vensim users may or may not know this. It changed the writing to lowercase. You saw me type it in uppercase, and it changed it to lowercase. That's just a quirk in Vensim. You'll see some magic here. So I'm going to define it, and I'm going to make it be 1,000. And what's my unit? And I'm going to do person. I don't like to do plurals typically. And voila, magic. It changed it back to capital letters, because internally, for those who didn't know this, Vensim has a switch that will change the case, upper lower case structure of an object based on what is in the object. Okay. let's go over to Studio and do the same thing. Studio has a separate construct, a separate picture for constants. And I'm a terrible typist, but I'm going to define it right here. Equals 1, 1, 2, 3. And again, syntax is painful. That's Studio's syntax for assigning a unit. When I hit enter, it says, hey, that unit doesn't exist. Would you like to create it? I say yes. And person and persons for plural. And then just hit finish. Now, the nice thing about this, at least from my point of view, is I have a running model in both softwares that does absolutely nothing. But it's correct. It has no unit errors. Units are okay. Yeah, well, this is a warning. Hey, you created a variable, but you don't do anything with it. And Studio doesn't do that. It uses that visual feedback. So if I were to define this guy and make a mistake here, let's get rid of one of those. It uses a visual feedback to tell you when things are incorrect or incomplete. I'll go back. I could have just, let's close that. I'll use the undo button. Get it correct again. Okay, maybe I should pause, speak up, chat, whatever you need to do. All right, now I'm going to go. Did I have any other constants? Does anybody remember? I don't know if Ram is still online, but he's seen this many times. I think there's a constant called growth rate. So I'm going to grab an auxiliary. Again, I'm going to type in capital letters. I don't have to. Then I go to and I define immediately. And if you remember, it was 1.1. So in Vensim, you would do this as 0.011. And the units would be 1 divided by year. I think Vensim capitalizes year. I can check the syntax. And that one seems to be okay, right? Notice it kept the capitals because it knows it's a constant. See, I'm a terrible typist. Growth rate equals 1.1. I prefer to use percent. Notice, again, syntax differences. Studio has a built-in unit called year, but it's YR. Vensim does also, but it's called YEAR. Done. Now I put my stock, and that is population, right? It doesn't like that. So I'm going to connect initial population to population, go back and define population, and the initial value, I'll just pick it from this list because I'm a terrible typist. And Vensim is still upset, and the reason for that is, in Vensim, this is a stock, but a stock that has no inflow and no outflow. So Vensim rules say it's not completely defined. That's just a quirk in Vensim. I'll do the same in Studio. Population. I'll grab the link. It's what this is telling me is, yes, you've linked it, but you're not using it. That's what the yellow pound sign. And this is saying, hey, you didn't give me a definition. So I'll open this guy. And I'd like you to look right here with your eyes, if you can read this, under the word unit. I will double click population. And Studio inherited the unit. That's what I meant by unit inheritance a little bit earlier in the slides. And then both, you'll see in Vensim in a minute, but both Vensim and Studio change the style of the arrow to say this is an initializer. It's not providing information throughout the model run. It's just an initializer. All right, and then finally we had a growth rate. Whoops, I clicked off it. I often do that in Vensim. Better delete it. Do it again. WTH growth, I'll call it. Get another connector, connect this to this, connect this to this. Move things around a little bit, maybe make this a little prettier. See if I can do that. There we go. And now I'll define growth. And growth is simply the growth rate times, that's another habit of mine. I like to keep spaces between operators times population. I do a lot of work in Vensim, but you probably can tell what's my obvious choice. All right, and population still acting weird. I'll do a check. Incomplete equation for population. How can that be? What? What happened to the whole definition? That's right, it's just the growth. Let me check syntax. Oh, and it says it's okay. That's another Vensim quirk, by the way. Notice the change in color here. That's to show it's an initializer. Let me do that quickly in Studio. Did it wrong. Sorry about this. I'm having, it's the demo effect, right? Growth, get my link or connector, link population to growth, and then link growth rate to growth. And go in here and simply say growth rate space times population. And it inherited the unit, figured it out. Done. 2 working models. I cheated a little bit. I didn't do the stop time, the start time, all of those kinds of things. Did not do that. So if we go back to the little session we did on archetypes way back in March or April, I was looking at the NIRA conversion problem and saying, are there examples of the archetypes, including limits to growth, in this whole process of converting old NIRA into new NIRA bills, currency? And we talked about a little bit about this simple model, which didn't go very far and is very mechanistic in some sense, just old NIRA becoming new NIRA at a certain rate per day of people trading them in. And we talked about some of the things that Laura hinted at, the softer variables, the lookups. Some people call them lookups, some people call them dimensionless multipliers, etc. And you'll have access to all of this, and I promise I will convert this to Vensim for you, and maybe someone who's a Stella user can volunteer to convert this model to Stella. And I can just run it. And remember, if you weren't at the earlier session, this is based on news articles concerning that currency conversion that Kalichi suggested might be a good problem. Okay, what I'm going to do in the chat, once I get out of these screens, is give you all the archetypes in Stella, Vensim, and Studio if you don't have them already. So let me minimize these guys. Here, do a stop share and see you. Okay, any questions right now? I know that was also quick. Also, I will put the archetypes webinar slides as a PDF, which is, I'll stick that also into the chat here in just if you give me a second. I should be able to do that if I can find it. So here, let's go with the, here comes the Stella archetypes. Give me a second here and I'll get the Vensim. Those of you who are Vensim users. And then finally the studio archetypes, which include, of course, the limits to growth that Laura talked about. And what else? Those of you who did not see the first video, there's the YouTube link to that. And I think that's it for right now. Put my video back on. Let's try a little something here because we have the power of Zoom. Down at the bottom of your screen, you'll see a reactions icon, a smiling face with a plus sign. If you open that, anyone who's taken a formal system dynamics class, please click the thumbs up if you've taken a formal class in system dynamics. I guess I have to click the thumbs up. They're starting to come through. Great. Okay. So the assumption then is for Laura and I, we're challenged because many of you have not taken a course before. You might not know what a stock, a flow is conceptually. So that I guess that's some information for the chapter, and maybe we can work together to do things that are even simpler than this, or at least provide you access to information, right? Those of you who know about the System Dynamics Society at systemdynamics.org, there are about 70 or 80 system dynamics courses listed there. I can't remember where exactly. I don't know if Kalichi was able to join us. I guess not. But there are a lot of courses listed there. There's a tremendous amount of free information that's not copyrighted. And of course, there's a lot of pirated information that is copyrighted and is available on the internet. And then if you're willing to wait until next summer, the Society does a very intensive summer school. You're given a month to work on homework problems, and then there's a 4-day, very intensive live session to discuss problems, work on models, ask questions, things of that sort. But I guess, you know, I'm trying to give a pep talk. Don't give up. Don't worry. There are lots of experts willing to help. There's lots of material. Maybe via the Nigeria chapter, we can handle that. But it's a long road. I've been doing this since, oh my gosh, I guess I am a grandfather too, since about 1992. And I thought that, gee, I'm a software guy. This should be kids stuff. It's just software, right? I can do it. And I learned my lesson very quickly, and then took the courses from MIT and in core system dynamics, and then a lot of topic courses, modeling the environment, strategy dynamics, advanced Vensim. I forgot all the courses I took. So please don't. Great, Laura, thanks for doing that. Putting the society site. Please go there. I'm not sure what it costs to become an official student member nowadays. I don't know, is it $45 or something like that? US dollars. But again, there's a lot out there that's completely free. There's also a mentoring system within the society. You can find that on the website if you search for mentor or mentoring. Think of anything else, Bunmi? Got about 10 minutes, it looks like.
Yeah, thank you so very much, Len and Laura. It's been very enlightening and insightful. I remember you sharing a paper some years back about naming conventions in system dynamics modeling.
Oh,
I
I can
believe that
do
will be
that
very
too.
helpful.
Let me
Yes, that
search
will
for
be
that
very
while you're
helpful for
speaking.
beginners. Yeah, it will be very useful and quite helpful for those that are starting off. That way you know how to label your models right from the onset. So if you could share that, it will be very helpful.
Yes, I'm looking for it right now.
The other thing I wanted to mention is if it won't be too much of a bother, if we could share your emails with participants, if they have 1 or 2 questions they want to chat you upon. I don't know if that is okay by you.
Yeah, it's okay with
If
me.
not, they could send. Oh, fantastic. Let me get you.
I'm still
Okay.
looking for that paper. I know it's
paper, right?
it's a D memo, what MIT called a D memo.
Okay, awesome. Laura has already shared her email. So for those on this call, if you have questions, you could just chat her up directly, send your questions to our email. Len is also okay with it, so his email will be dropped in the chat box. It's been we had to manage time, so there's only a little we could do in this hands-on session. But I'm certain that the foundation has been laid, so anyone that is interested could definitely pick it up from here. The recordings are available on Society website. If you go to Society website and you click on Nigerian chapter, all the videos of past sessions are also available there, so make use of this opportunity. So that will be very helpful for everyone if you're interested. I do not think there's any other thing we need to talk about for now, so unless there are other questions, and I've looked through the chat, all the questions in the chat box have been addressed. The email addresses of both Len and Laura in the chat box. Please avail yourself of this opportunity to reach out to them if you have questions.
I have a question for Laura,
So I'll just
actually.
leave. Oh, awesome.
Yeah,
Please
go ahead,
Len.
Hey, Laura, do you know anybody in agricultural economics at MSU?
I do, including my husband. What are you?
No,
what-
Scott, who's the chair.
Oh yeah, Scott. He's not. They just got a new chair, but yes, I know
Okay,
Scott pretty well.
he and I got ag econ degrees together at Purdue.
Oh really? Oh, that's so
And-
funny. Small world.
Yeah, and went to Niger together
Right.
when he
Okay.
was a grad student, and I was doing some consulting for the ag econ department.
Oh, that's so funny. Okay, I'll tell him I ran into you when I see him.
Yeah, we had some really good times.
Good.
And then for all of my the way I like to say this is colleagues, friends, and soon to be colleagues and friends in Nigeria. I don't know if you know this, but I lived in Niger for a little over 2 years, and I learned to speak Hausa. So
Yeah, awesome.
all I can say is say Anjima.
You tried. That's really nice.
Oh, let's see. We have
Yeah.
a question. Ainde.
Yes, please. Thank you very much, Len and Laura. Very interesting presentation. Of course, I take advantage of any presentation I see, and I've picked up I particularly like the idea of showing all the different. I love the way Len did it. And I also love a kind of guide to presenting to parents. So I'm about concluding my PhD, and I'm using system dynamics methodology. So I would love that I have a guide like that for my writing my report. I love that guide on how to present to client. So I would love to have, because I'm a mechanical engineer, so my supervisors are so much interested in equations, and I've got, like Len described it, spaghetti, so much of spaghettis. I don't even know how to report that. I have a lot of difficulty reporting. Len, Laura, anybody?
Len, I think the question was maybe for you. It sounded like you faded out a little bit there, Ayinde, but I think the question was about how do you report on the variables and equations in your model in a standard way. And Len, you had mentioned that.
Yeah, how I will report, especially I'm a mechanical engineer, so my supervisors are interested in seeing. Okay, so I have a lot of models, sub-models that I'm finding difficulty putting in my reporting in my final write-up. You didn't get it?
So Len, we can't hear.
Sorry, I was muted. Everything,
okay.
Everything that's available, at least the big three, all of them have a way to export equations, right? So you're going to have to do some searching, because I'm not familiar with Stella. But for example, here is, hopefully you can see the screen now. Here's a listing of the equations from the studio model on NIRA.
Yeah, okay.
Okay, and then all of them have features like, what do you want me to show? Do you want me to show the value of the variables? Do you want me to show the type of the variables? And then they either export as comma separated values or text, or maybe even Excel format. And that way you can, if people want to verify that indeed you're doing a good job, they can see that. One issue we find with publishing is sometimes peer reviewers will ask for the model. And if you have a model that's got, like one that I worked on, it had 3,300 variables and 8 million pieces of data in it. There's no way that a peer reviewer can manage that, and they might not own the software. So that becomes a problem that you have to deal with. But maybe if you just give them an equation listing like the one you're seeing here, let me see if I can bring up the Vensim. Vensim has a view called, well, this is the new Vensim format, and now I can't.
Sorry, Len, maybe I should reach out to you later so that I don't.
Yeah. But every good tool has a way to export.
I'll reach out to you. I'll reach out to you.
Yeah. No problem.
So that we don't take other people's time.
Yep.
Thank you very much.
And that, don't forget that last page. I'll be sending this to Bunmi. That page of the prose, the text description. What did I do? Who were my clients? What's the time bounds on this model? It's also good for you to keep track of, as you're working, what's useful and what's not useful. Oh, there it is. Stella has an equation viewer. You can export it.
Yeah, and I'll just, Len, you're talking about this, but in system dynamics, the modeling philosophy is that the really important thing is the model structure.
Yes.
So the equation, you can have all the quote correct equations in the model, but if it's not representing the system in a way that is helpful and is reflective of the actual dynamics, then it's useless, right? So we always want to check the model structure as well as the
Yes.
equations. Yeah.
Yeah. And, you know, large models start out as very small models, so you have to build incrementally. But that's a really good point. Structure
Yeah.
determines behavior.
Mhm.
Thank you. Thank you.
Yeah, that's very true. Thanks, Len.
And,
Thanks,
and
Laura.
the other thing, Bunmi, I should mention, I don't know if any of you know Kude. I didn't see him here
Yeah,
today,
sure. Yeah,
but he also is
not
a
here
good,
today.
yeah,
But
he's a good
with us.
source. He's a good source of SD skill in Nigeria.
Yes,
Yeah.
we're together. He's with us on the chapter. I don't know
Okay.
why he couldn't make it today, but he's with us. We're in contact.
No problem. He's seen
Yeah.
enough of me.
Imagine.
We await the slides, your slides.
Yeah, yeah.
We got
I'm,
that from Laura already.
yeah, I'm going to prepare that as a PDF and send that. Maybe I can do it right. How much time have we? We're right at time. I'll send it to Bunmi and Kalichi, and then they
Okay,
can
thank you.
distribute.
The meeting recording will be available on the System Dynamics Society. Just go to Nigerian chapter, and then they're also available on YouTube. I can see a question in the chat about that. They're available on YouTube as well. I would for those that have my contacts, those that have the chapter email, you could just request and then we'll share with you for those that request for it. But the link is available online. Once you click on YouTube, it takes you straight to the page. You can view, watch over and over. You can replay at your convenience and try to follow the steps. Thank you so very much.
Oh, Bernard's got a question, Bunmi.
So can I have only a short question?
Just in the nick of time. And
So
did I hear a question, please?
yes, please. So only a
Okay,
short
fine.
question. So maybe this is more advanced, but the question is when you make bigger models from and can you encapsulate those smaller models also? Is there a possibility in these softwares?
I know that both Stella and Studio allow, the term might be component. Maybe generically it would be called a submodel. So you can encapsulate and send values back and forth across. Vensim used to have macros, which is something like that, but I don't think it does as well as Stella and Studio do in terms of components or modules. Oh, maybe I should mention, Laura, and I haven't kept up with Karim and Bob at IC, but the vendors have lots of free videos.
Mm-hmm.
The vendors of the software themselves. So they're not going to teach you a lot of methodology, but they will teach the syntax. How do I do this with that? But not a lot of conceptual content, but a lot of syntax content.
Yeah. I mean, the other thing I really appreciate about Stella, I think the help menu is excellent, you know, so I mean, that is it costs money, but if you download it, you get access to the online help menu and it really is great. It goes through like, here's what this is, here's how you do it, here's how you set up the equation. So Bernard, yeah, just to shortly answer your question, yes, all the softwares have those capabilities. Yeah.
Thank you very much.
And Studio also has what's called context sensitive help. So if you have an equation and you click on a keyword, it'll automatically open that help to that keyword, which is pretty slick. Okay, Bunmi's in charge.
All right, that's great. We don't want to spill over anymore. For further questions, please feel free to chat them up via email, or you could mail the society Nigerian chapter. We'll take on questions as well and forward them. If we can handle them, we will. If not, we'll forward them to Len and Laura. And hopefully, if we call on you next time, you will still answer us. Is that a yes?
Yeah.
Thank you. Thank you very much.
All right. Thank you
Thank
so
you all
very
for
much.
coming.
Yeah. Bye, everyone.
Bye.
Thank you.
Bye-bye.
Yes, I just want to say to Len Mungo Day. Say and